Assalamu alaikum. Welcome back to the lecture. Today we'll discuss lecture number 2, which is based on signals and systems. So a signal is a description how one parameter varies with a variable, and a system is a process that produces an output signal in response to an input signal. So here is an input signal x of n. It passes through the system and it gave an output y of n. So system in mathematical form is written here. Y of n is equals to 1 by f summation of x of n from 0 to 4. You can see it is an averaging system since it has 5 samples and is divided by 5 afterwards. It is a representation or an example of a system. We'll here study different operations on signals, flipping, shifting and scaling. Suppose there is a signal x of n. Flipping means when you multiply an index with the negative sign, it flip your signal that way that the positive values turn into the negative side and negative values come in the positive side. So here is the mathematical representation. You will find the values by putting the index in here, and graphically you can see here that -1 and -2, its value was -1 and +2. In the flipped signal, these values are now in the positive side and these values are now in the negative side. So that's how flipping works. Now let's discuss another property, that is shifting. Shifting is when you add a number in the index. So when you add a positive number in an index, you can do some calculations here. If you are finding y of -4, you add an index 2 and you get some value. You can check in the signal. In -4 there is no value, it is 0 in here. But in the shifted signal, you got +2. So that's how it works. When you shift a system on the positive value, the range of the signal in the negative side increases and the range of the signal in positive side decreases. You can see now that y of 1 is equals to 0. We had a value of x of 1 in here. Now you can check this in the graph too. You can see that the whole signal shifted in the negative side. There were 2 samples in the positive side and now they're in the negative side because we added 2 in the shifted in the signal index. So it is called backward shifting because the signal is moved backward. If we added a negative number in the index, our system would have moved forward. We can see its example as there is an example of a forward shift x of n -3. Calculation shows that when you add -3, it becomes x of -7, and we know there is no value at x of -7. We store values from -2. But when we go to the positive side, x of 6, when you -3, then it is x of 3. No, in the 5 minus 3 is x of 2. It is -2. So in here you had no value on index 5, but now you have a value on index 5. So you get more values or more samples on positive index, and you get less values or less samples in the negative index. That's how we can say that our system has moved forward. Graphically you can check it as follows. In here you can see there is no difference in the amplitude of the signals and samples. Just check that system has moved forward. Okay, so the value at 2 is now at 5, the value of 1 now is 4, the value at 0 is now at 3, and value of -1 is now at 2, and -2 value is now at 1. So that's how shifting works. Let's discuss another property of the signal, that is scaling. Scaling is when you multiply some number, some integer with index n. So you can see that when you multiply an index, y of -4 is now y of -8. x of minus 8, sorry, x of minus 8, and we know there is no value at minus 8. Y of minus 1 is now at x of minus 2, and we have 2 over here. So on, you can do mathematical calculation by yourself. You can check the output. You can see that there are no values at minus 2 and positive 2. Their values are terminated because when we multiply it with 2, the value at the value of minus 2 is gone. So this type of scaling, we call it compression, because it compressed our signal. When you multiply some number with index n, you are doing actually compression. Okay, let's take another example of scaling. You can divide a number and index with a number in scaling too. So we did some mathematical calculations over here. Y of 1 is equals to x of half, which is 0. Over here you can check there is no value on 1 by 2, and y of 2 is equals to 1. So there are more zeros added, but the number of samples are increased. So that's why we called it expanding a signal. You can check it over here that now our range is increased from minus 2 to minus 4 and 2 to 4. The equal increase in the range, but there are more zeros added in here. So this is called expanding a signal. Let's do another example now. This is a system in which we have to do all of the properties: flipping, scaling, shifting. So let's divide our process in 3 steps. First of all, let's do flipping. Okay, we should know the sequence of using the properties. Okay, first of all you do the flipping, then shifting, then scaling, if you have to do all of them. Now in the signal, we'll first do the flipping. Z of n is equals to x of minus n. Okay, let's see here. It is 0th value, and these values are at negative index, and these values are at positive index. So when you flip the signal, the negative values will come to the positive side, and positive values will go to the negative side, as you can see here. Okay, now we have to shift the flipped signal. Z of n, we'll shift Z of n, not x of n now. Okay, when you do shifting, I have told you that when you add in an index, you are moving it backward. So we are adding 3 in here, so our 0 is at 0. Now it will move 3 steps back. Okay, 1, 2 and 3. It will now be at minus 1. So this is our 0th value, and all these values are at negative side. This is called backward shifting. Now scaling. I told you that when you scale a signal, you are actually compressing it when you are multiplying with an index. So you get less values. You see that even values will be gone. For example, this value 2, 0, minus 2. They won't be here anymore because odd values, because when you multiply with 2, they become even index. So even index in the this signal, shifted signal, will be the output of the scaled signal. Okay, that's how we did this example. Now arise a question that whether we can recover our expanded signal or not. So there are some methods, algorithms, which we use for recovering our expanded signal. Okay, first of all we use zero order hold. In zero order hold, we assume the same values in the missing parts. That is, if at minus 6 there is positive 2, we'll assume that at minus 4 and minus 5 there is positive 2 value. Meanwhile at minus 2 and minus 1 there will be negative 2. Same as here, we assume that missing parts carry the value of given parts. But this is not an efficient method. It doesn't recover the original signal at all. So we use another method, first order hold. We use linear function to interpolate missing parts. That's how we can recover our original signal a little bit better. We use these equations, the equations of linear line. So this is not exact method at all. We have to, sometimes we use second order hold to interpolate our missing values. So that's a bit better. Now let's check the relation between step and impulse function. First of all, we all know that impulse function is a function which gives 1 at 0 and 0 at all other values, and step is a function which gives 1 at all positive values including 0. Okay, so this is a relation between impulse and step function. We get a impulse function when we derivate the unit step with time, and we get unit step function when we summation when we do summation or when we integrate impulse function. Okay, we can see it here. We know that impulse function only gives one value at a time, so we add a shift in here and sum all the impulse functions to get a unit step function. So u of n minus 1 is equals to delta of n. That's how it goes. Let's check example. This is how we can split our signal into delta function. We know the delta of n is equals to 1 at 0. So 2 delta of n will be 2 at 0. And delta of n minus 1 will be shifted version of delta of n. That means now we get 1 at 1. Shift of minus 1. And we'll get minus delta of n minus 2 when we shift the delta function by 2 and invert its amplitude to make it minus 1. Same as here. 3 delta of n minus 3. We get value at 3 and amplitude at 3. So that's how we splitted our function in the impulse form. We can write it as here, the same thing, x of k into delta of n minus k. Okay, and we do its summation. That's how we get our original signal from frequency domain. Now let's discuss even and odd decomposition. We discussed impulse decomposition right now, but now we'll discussing even and odd decomposition. It is very simple. Formulas are given. When we add function signal and impulse signal in flipped signal and divide it by 2, it is an even decomposition. And we subtract signal from its flipped signal, it is, and divided by 2, it is an odd decomposition. We did the same decomposition. We did the decomposition with the same signal that we split it in the impulse form in here. There are some calculations involved which you can easily do on calculator. So I didn't bother to write them down. That's how the graph will look like. Same with the odd decomposition. These will be the values, and that's how the graph will look like. That's all from lecture number 2. Hope you enjoyed the video and see you in the next lecture. Allah Hafiz.